In our last module, we have discussed series of functions and their convergences. In this module, we shall discuss one particular series which is known as power series, that is some series involving different powers of x. We shall discuss their convergences and their applications in statistics. We also discuss radius of convergence, interval of convergence for such series. Finally, we shall discuss Taylor series expansion, which is some application of power series, and using the results of power series we shall discuss convergence of Taylor series for both univariate and multivariable cases. In this module, we shall discuss power series, their convergences, and lastly Taylor series and their applications. Power series is a particular type of series of functions. Most of our discrete distributions like binomial, Poisson, negative binomial are actually a convergent power series. In addition, we use different generating functions like moment generating function and probability generating functions, which are also power series, and we often use some limit operations or differentiation on such generating functions. However, the existence of some generating function can be justified from the convergence properties of power series. We often deduce moments from the moment generating function using successive differentiation. So, convergence of power series validates such operations. So, what is a power series? Actually, a power series is a series of functions where the nth term is nothing but fnx, which equals an multiplied by x minus c whole to the power n for every n greater than or equal to 0. So, using this nth term, we get a power series around c. However, for simplicity, we take c equal to 0. Naturally, a power series does not always converge for every x, but it always converges to a naught for x equal to c. For example, summation n from 0 to infinity x to the power n divided by n factorial, which is nothing but the exponent, the e to the power x, converges for every real x, whereas the series summation n factorial multiplied by x to the power n converges only for x equal to 0. So, let us discuss convergence of power series. So, in general, consider the power series an summation n from 0 to infinity an x minus c whole to the power n for x belonging to some set A. Assume that one of the following limits exist. Note that here the limits may be infinite. Number 1, limit of absolute value of an plus 1 divided by an as 1 by r, and limit absolute value of an whole to the power 1 by n is 1 by r. Then the power series converges absolutely for all x such that absolute value of x minus c is less than r. The power series diverges for all x satisfying absolute value of x minus c greater than r. In addition, the power series converges uniformly and absolutely for every subset of c, c minus r up to c plus r. So, let us define radius of convergence. R is defined as a limit. So, this r is called the radius of convergence of the concerned power series. The interval minus r to plus r is called the interval of convergence of the power series. R equal to 0, we conclude that the power series is nowhere convergent. However, if r equal to infinity, the power series is said to be convergent everywhere. Every power series can be differentiated term by term within its interval of convergence, and every power series can also be integrated term by term within its interval of convergence. Actually, the first derivative of a power series is also a power series with the same radius of convergence. So, term by term differentiation is possible, and the same can be said about the integration, about the integrated value of the power series. So, let us illustrate our idea using some examples. Consider the power series x plus x square plus x cube plus x to the power 4 up to so on, which is nothing but the so called geometric series. However, this can be alternatively interpreted as a power series with an equal to 1. Now limit of absolute value of an to the power 1 by n equal to 1, and hence the power series converges absolutely for all x such that absolute value of x less than 1. Thus the radius of convergence is r equal to 1 and interval of convergence as -1 to +1. It is already noted that the series diverges for x equal to plus minus 1, and hence the open interval -1 plus 1 is the exact interval of convergence. So next, consider the power series with nth term minus x to the power n divided by n. In this case, an is nothing but -1 to the power n divided by n. Now limit of absolute value of an to the power 1 by n is nothing but 1, as limit of n to the power 1 plus 1 by n can be seen to be 1, and hence the power series converges absolutely for all x such that absolute value of x is less than 1. Thus the radius of convergence in this case is 1 and interval of convergence as -1 to +1. However, for x equal to -1 we get the so called harmonic series which diverges. Again, for x equal to +1 we get the alternating series which converges. Thus we get the interval -1 to +1 where -1 is excluded from the interval and +1 is included in the interval is the exact interval of convergence. So consider our next example, which is summation n from 1 to infinity x to the power n divided by n factorial. This is the well known E series and is also a power series with an as 1 by n factorial. Now absolute value of an plus 1 divided by n has the limiting value 0, and hence the power series converges for all x belonging to the real line. Thus the radius of convergence in this case is plus infinity and interval of convergence is nothing but the whole real line. Consider our next example, which has the nth term as n factorial multiplied by x to the power n. So this is a power series with an as n factorial. Now the limiting value of absolute value of an plus 1 divided by an is infinity, and hence the power series does not converge for any x belonging to the real line except for x equal to 0. So in this case, radius of convergence is defined as r equal to 0. Consider our next example, which is again a power series, summation n from 1 to infinity x plus 2 whole to the power n divided by log n. So this is a power series centered at c equal to -2 with an as 1 by log n. Now absolute value of an plus 1 divided by an has a limiting value 1, and hence the power series converges for any x such that absolute value of x plus 2 is less than 1, or for -3 less than x less than -1. Thus the radius of convergence in this case is r equal to 1 with interval of convergence as -3 to -1. However, for x equal to -3 we get the series summation -1 to the power n divided by log n. Since 1 by log n is a decreasing sequence with limit 0, then by Leibniz test we find that the series converges. However, for x equal to -1 we get the series summation 1 by log n, which by condensation test diverges. Hence the exact interval of convergence in this case is -3 to -1, where the point -3 is included in the interval and -1 is excluded from the interval. Consider our next example, summation n from the power series summation n from 2 to infinity n factorial x minus 1 whole to the power n divided by n to the power n. So this power series is centered at c equal to 1 with an as n factorial divided by n to the power n, for which is defined for every n greater than or equal to 2. Now if we take the ratio an plus 1 by an, we get the limit of the absolute value as e, and hence the power series converges for any x satisfying absolute value of x minus 1 less than e, or for minus e plus 1 less than x less than e plus 1. The radius of convergence in this case is r equal to e, with interval of convergence as minus e plus 1 up to e plus 1. However, separate examination on the boundary, that is on x equal to e plus 1 and x equal to 1 minus e, can be carried out to know the exact interval of convergence. So, next consider hypergeometric series. The form is given in the slide, where alpha, beta, gamma and x are all positive. So, naturally this is a power series with nth term given as in the slide, and after little bit manipulation we find the limiting value of an plus 1 divided by an as 1, and hence the power series converges for any x satisfying absolute value of x less than 1. The radius of convergence in this case is r equal to 1, with interval of convergence as minus 1 to plus 1. However, convergence on the boundary depends on alpha, beta and gamma. So, next we pass on to our next topic, which is very closely related to power series. This is actually a Taylor series expansion. Actually, a Taylor series expansion is one of the most useful tools for a statistician. A Taylor series provides a power series representation of a function using its higher order derivatives. It is extremely useful for obtaining the large sample distribution of different implicit or explicit functions of relevant statistics. For example, if we want to find the distribution of say xn multiplied by s square, or say just for simplicity assume we are just interested to find the large sample distribution of xn bar to the power 3, then we can use Taylor series expansion of the function x cube, and then show that higher order terms tends to 0 in probability, so that the problem boils down to finding the asymptotic distribution of a simpler term involving x bar. So, that's in this way Taylor series expansion is very useful in at least in large sample theory. So, we start with the formal definition of a Taylor series. So, we start with Taylor's theorem. Let f(x), x belonging to closed interval a b, be a function defined on the real line such that the kth order derivative of f(x) is continuous on the closed interval for all k less than or equal to n minus 1, and the nth order derivative of f(x) exists on closed interval a b. Then for any x naught belonging to a b, we have the representation f(x) equal to Pnx plus Rnx, where Pnx is defined as summation k from 0 to n, the kth derivative of f(x) multiplied by x minus x naught whole to the power k, whole thing divided by k factorial, where f naught x is defined as the original function f(x), and Rnx is defined as if the n plus 1th order derivative of f evaluated at c multiplied by x minus x naught whole to the power n plus 1, whole thing divided by n plus 1 factorial, where c is some point between x and x naught and is represented as a linear convex combination of x and x naught, which is tx plus 1 minus tx naught for t belonging to closed interval 0 1. Here Pn is called the nth Taylor polynomial for f at x naught, and it is reasonable, and it is a reasonable approximation to f for points near x naught. Rn is called the remainder term in Lagrange's form. However, if limit of Rnx equal to 0 for all x belonging to open interval a b, then limit of Pnx comes out as fx for all x. Thus, f admits of the Taylor series expansion, which is summation k from 0 to infinity, the kth order derivative of fx multiplied by x minus x naught whole to the power k divided by k factorial. If x naught equal to 0, the above is called Maclaurin's expansion of fx. However, convergence is difficult to check. The convergence is difficult to check for a Taylor series, and hence we need some simpler sufficient conditions. So, consider the nth term, which is the nth order derivative of fx multiplied by x minus x naught whole to the power n divided by n factorial. Now, the series with nth term x minus x naught whole to the power n divided by n factorial converges for all x. Thus, if we can show that the nth order derivative of x is bounded by some finite number m for all x in some interval around x naught, the convergence can be asserted for that interval. So, first consider the function sin x and assume x not equal to 0. Now, the nth order derivative of sin x is known to be sin n pi by 2 plus x. So, in this case, the remainder after nth term, that is Rn x, comes out as sin n pi by 2 plus x multiplied by x to the power n plus 1 divided by n plus 1 factorial. Now, since sine functions are uniformly bounded by unity, we find by the condition just discussed earlier that the Taylor series converges to the sine function on the real line. The same can be said for cosine function, as the nth order derivatives of cosine functions are also uniformly bounded by unity. Next, consider log the function fx as log 1 plus x and assume x not equal to 0. In this case, using some induction, the nth order derivative of fx can be obtained as minus 1 to the power n minus 1 multiplied by n minus 1 factorial whole thing divided by 1 plus x whole to the power n. Then the Taylor series around 0 can be expressed as minus 1 to the power n minus 1 x to the power n divided by n, obviously with a summation. Suppose we wish to know whether the above series converges for x equal to 1. Then we get after a little bit algebra that absolute value of Rn1 is less than or equal to 1 by n, which tends to 0, and therefore the series converges for x equal to 1. Thus, we get the representation log 2 as summation n from 1 to infinity minus 1 to the power n minus 1 divided by n. We next pass on to our next topic, which is multivariate Taylor's expansion. Actually, a multivariate extension of the Taylor series is perhaps even more useful in practice. To illustrate the results, let us introduce some notations. For the first notation is nabla. The first notation is gradient operator nabla. That is, if we have s variables x1, x2, xs, then the nabla operator gives us a vector with the gradient of the function. That is, by nabla of f, we get a vector with elements delta partial derivative of f with respect to x1 up to partial derivative of f with respect to xs. So, with this notation, we can express multivariate Taylor expansion. Let f be a function with s variables, and suppose there is a neighborhood of a such that f and its up to L plus 1th partial derivatives are continuous in that neighborhood. Then for every x belonging to that delta neighborhood, we have fx equal to fa plus summation k from 1 to L 1 by k factorial multiplied by transpose of x minus a multiplied by the nabla operator whole thing to the power k, and this is just acting as an operator of on fa, plus 1 by L plus 1 factorial into the operator x minus a transpose multiplied by nabla whole to the power L plus 1 of fz, where z is as before a linear convex combination of a and x, that is z equal to 1 minus t multiplied by a plus tx for some t belonging to 0 1. However, Taylor's expansion of second or third orders are most useful in practice. Such expansions can be expressed in terms of Hessian matrix. So, if we consider just the second order Taylor expansion, we get Fx as Fa plus the first derivative of f with respect to x, which is a row vector multiplied by x minus a, plus half into the quadratic form x minus a transpose multiplied by the Hessian matrix of f multiplied by x minus a, where as usual z is a some point between a and x, that is z can be expressed as 1 minus t multiplied by a plus tx for some t belonging to 0 1. However, lastly we note that the higher order terms of a Taylor series expansion can be expressed in terms of big O and small o notations, but those things are beyond our scope of discussion. So, we just skip those details. So, we have just seen the importance of power series, their convergence, and how to check convergence of power series, and also expanding some function with satisfying some suitable conditions using a Taylor series. We also discussed multivariable case of Taylor series expansion and introduced some expressed such Taylor series expansion in terms of big O and small o notations defined earlier.